Hello students, today we will read about electrostatics of conductors. Like previously, we have learned about what are conductors and what are insulators. We have defined a third category also, that was semiconductors. Third category was semiconductors. So what we have previously read about these conductors, insulators and semiconductors, we will just go through, know the definition, and then we will start with our today's topic, that is electrostatics for the given conductors. Now the conductors are mostly having the mobile charge carriers, and they tend to conduct the heat and electricity. They tend to conduct heat as well as electricity. But as we are talking about electrostatics, electropotentials, electric fields, electric charges, so much all about electric. So we will here only read about the conduction of electricity and various other components related with the electricity, nothing or more than that. So we will define our conductors with respect to electricity as the points or the things, the objects which have ability to conduct electricity via them are the conductors. Insulators are the objects which do not allow the conduction of any electricity or heat. They do not permit, they are like barriers. Insulators do not allow any conduction. Why so? What is the difference that makes a conductor to conduct and insulator to insulate? The main difference is the charge carriers present in a conductor and in an insulator. Insulator do not have mobile charge carriers which can travel from a point A to travel to the point B, whereas conductors have mobile charge carriers. So as this charge are mobile, they tend to move from here to there, and when they are moving from a particular point to other point, they carry this electric as like this electricity as their one of the feature, or the heat. All these things, like heat is a kind of an electromagnetic wave which is transferred by these mobile charges only from a point to another, as well as electricity is the motion of the electrons. So any charged particle, it can be electron. So electron is also a negatively charged particle. When it moves, this is seen to be as moving electricity. Now the third class is semiconductor. What is a semiconductor? Something which have ability to conduct but partially. Semiconductors can conduct electricity as well as heat but partially. Conduction possible but partly or partially, anything. Okay. So these semiconductors have varied properties, and these comes from the group 14 of our periodic table, and they are like doped with group 13 and with group 15 to make like pentavalent and trivalent semiconductors. I'll just write over here pentavalent or trivalent semiconductors. When they are doped with group 13, they are trivalent, and when they are doped with group 15, they are pentavalent. This trivalent and pentavalent creates the excess of a charged particle. These charged particles tend to move in the semiconductor and make a semiconductor conduct, make a semiconductor have the conducting property, behave as conductor. So this semiconductor, when seen as a pure, when there is no these dopants included in our semiconductor, what basically happens, this semiconductor do not show such kind of property or behavior. Once we are doped, they will show the behavior of a conductor. There are many basic differences when we read about semiconductors and conductors, like their temperature dependence is different, their pressure dependence is different, the way they behave is different. In conductors we have like single kind of charge which is moving from here to here. In semiconductors we tend to define two different charges, one is a virtual and one is a real charge. So semiconductors will be discussed later in the class. For today's conductor are main, so we will go and start our class, that is electrostatics of conductor. The basic of conductor is understood, something which tend to conduct electricity. So mostly all the metals come under the group of conductor, but noble metals like orium. What is orium? Orium is chemical name of gold, silver, these platinum. These are the noble metals which have low conductivity, or at normal temperature and pressure they do not tend to conduct any electricity. Okay, so if we are varying their composition, if we are varying the pressure and temperature for them, they will definitely they will show some conduction, but not as good as copper, iron or aluminium or these kind of metals are showing. So these metals are basically termed as noble metals. Noble metals which do not try to get engaged in such conducting, and they are silent. Even though a lot of electricity is being passed through them, they will not try to like transport it to another end, right? So now starting with our electrostatics for our conductors. First thing in the introduction they have mentioned the properties of a conductor. See the point number 1. Conductors contain mobile charge carriers. As told, there should be some mobile charge carriers, and in case of conductors specifying it, the charge carriers are the loosely bound electrons. Charge carriers are loosely bound electrons. In metallic conductors, these carriers are electrons. In metals, the outer valence electrons part away from their atoms and are free to move. What exactly they mean is, see, we are having one nucleus over here. We will denote it with a plus sign, and then we have orbits. In these orbits we have electrons revolving. The orbit which is closer to nucleus, orbit closer to nucleus, like as you have read in chemistry, we define these orbits as K, L, M, N and so on. Okay, so K is the nearmost orbit to the nucleus, and the interaction of, or the attraction of the nucleus and the electrons, attraction of the nucleus and electrons is very high in this region, very high in this region. Now if we go with L, it will be little lesser. If we go for M, more lesser, and for N it is quite less. The interaction between the nucleus and the electrons present in the N shell is quite less. So what basically happens in this region is that these electrons which are present in the nth shell are termed as loosely bound electron, loosely bound electrons. So these loosely bound electrons are free inside the metal or the metallic conductor, are free to move around, but are not free to get out of the this orbit or this particular shell. They are not free enough to jump off the metallic orbit. Fine. So these electrons which are able to move from here to there tend to conduct the electricity in the metal. Coming to the fourth point here, these electrons are free within the metal but not free to leave the metal. Free electrons form a kind of gas. They collide with each other and with the ions and move randomly in different direction. What this gas is? Basically, when we read physics more than what is written in NCERT, we get to know that gases which are kind of clouds, and these clouds are termed as electron clouds. electron clouds. Like here we have so many electrons in the outer shell, outer shell. What exactly is having? They are forming a gas-like structure. Like in the gases we have so many particles, they also behave like so many particles, showing random motion, random motion. Now what happens when they show random motion? These kind, like first thing which we know, this structure is known as plasma of electrons. They are in a semi-solid form, like a gaseous, and tend to have random motion here and there, and this random motion tends to have a non-uniform structure of these electrons in the outermost orbit, because there is no external force aligning them, no external force aligning them. Okay. Now what we get to know that these electrons which are present in the outer shell are moving in a random motion. Now we put some external electric field and make them drift in the direction of the field, and everything will be then aligned in the direction of electric field. Like see, our plus minus, and this is again plus minus, right? Now we have given us a electric field. This is in the presence of no electric field. Electric field equals to 0. Now second case is when we gave electric field which is not equal to 0. We gave electric field. This electric field is going from here to here. What will happen? They will these charges will be aligned along the E. Now see, this is a random motion. This is going like this. This is going like this. This is going like this. But see here, everything is going as the electric field is going. This is called alignment. Alignment along E. Okay, E is electric field, and we define E with a vector or a like arrow mark on its head. That is a vector format. Always make sure wherever you are defining or writing E in the symbolic form, put this head arrow. It's very much compulsory. It gives the property of our electric field. So in an external electric field, they drift against the direction of field. Positive ions made up of nuclei and the bound electrons remain held in their fixed position. This is a very much important point. This property in the presence of electric field and in the absence of electric field, these two different properties are being shown by loosely bound electrons. But this nucleus of our this metal, like we were dealing about this metal, see this metal, in this metal, this nucleus and this K shell or L shell, the shell nearer to the nucleus, these electrons are bound electrons which are bound to nucleus due to attractive forces in this nucleus. They will be unaltered in the presence of external electric field. They will be unaltered in the presence of external field. Only the loosely bound electrons or the outer shell electrons which have very less, or we can say extremely less, attractive forces towards the nucleus will be aligned and will be affected by the given external electric field. So this is important. Make a note of this particular point, that the positive ions which made the nucleus and the bound electrons which are near the nucleus and are held by the attractive forces of nucleus will be fixed in their position. Only the position will of the loosely bound electrons will drift along the direction of electric field or the external electric field that's been provided by us. Coming up to the next point. In electrolytic conductors, the charge carriers are both positive and negative ions, but the movement of charge carriers is affected by both external electric field as well as also by chemical forces. Electrolytic is a chemical and is a solution as well as is a solution. We add these electrolytes in a solution of the same electrolyte and then they show dissociation into positive and negative ion. Water can also be a electrolyte when the external electric field is provided. This is our water H2O. When E is provided through it, this H2O molecule divides into H plus and O minus molecules. They called ions, H plus and O minus ions. So these ions, both these ions travel from here to there and conduct the electricity. So carriers is affected, like both positive and negative ions. Here the charge carrier is both positive and negative ions. I have given you a very simple example of water. Another example which I can give is HCl, that is hydrochloric acid. In that the ion formation is H plus and Cl minus. Another one which we can take is H2SO4, where H plus and SO4 2 minus are the ions. So these kind of electrolytic solutions are there. We take zinc chloride also, copper sulfate also, zinc sulfate also as to form the electrolytic solution. So these are commonly used electrolytes. Water is the most common because of the polarity it have and availability it have, easy, and almost all, like it have a very good conducting property for electricity too. So these are the things, and as this is a chemical solution, external electric field, of course it will play a very major role, but the chemical forces also play a very positive role and important role in this electrolytic solution formation and the conduction of electricity through the electrolytic conductors. So now we will record the notes and results regarding the electrostatic of conductors. We will not talk much about the chemical forces because this is out of the physics scope. So we have, as we are reading the physics, for us most important thing is to know what is the electrostatic properties of a conductor. So moving on to the electrostatics of conductor. The first property of the conductor is, inside a conductor electrostatic field is zero. Inside a conductor electrostatic field is zero. So this is our conductor. In this, E tends to be 0. See, we considered a conductor neutral or charged. It can be neutral, it can be charged, it doesn't matter. Now external electrostatic field may also be present. We are not saying that this external electrostatic field is not there. We say that we have some external electrostatic field also. E, external is there. Okay, this conductor is either neutral or charged, it doesn't matter. Okay, neutrality doesn't matter, being charged doesn't matter. Okay, now in the static situation, when there is no current inside or on the surface of conductor, the electric field is zero everywhere in the conductor. It's very much clear. Okay, like this is a static situation and there is no current flowing inside the conductor and on the surface of conductor. In both the cases there is no current inside or on the surface, hence electric field is zero everywhere. Even on the surface it's zero, on the surface it is zero. This fact can be taken as a defining property of a conductor. A conductor has free electrons. As long as electric field is not zero, the free charge carriers would experience force and drift. In this static situation, the free charges have so distributed themselves that the electric field is zero everywhere inside. So electrostatic field is zero inside the conductor. So see, I'll explain in a better diagram the whole concept. We are having a charge, like we are having a conductor. It can be charged or neutral. It doesn't make any difference. Now, in the absence of electric field, everything is as such, but now we have provided some external electric field. E external is provided. As soon as we will provide E external, what will happen? Before providing E external, the charge carriers were in random motion. Before E external, electrons were in random motion. Now we provided, after E external is provided, electrons aligned in a direction. Okay, the electrons which are over here are aligned in a particular direction. Now while they were aligning, they were moving. Hence they were producing a current while aligning. Okay. Now after some time, what happens? Electrons have aligned. Now everything is static. So once they are static, there is no flow of current. When they were aligning, there was flow because the charges were flowing, the electrons were flowing. But once they have aligned, it's been static. Now as it's been static, what exactly is happening? That there is no production of electric field on the surface, on the inside of conductor. Just on the surface, because these charges are property of the surface, not inside. There is no charge present inside. Mein no charges are available. Q inside is zero. Okay, the charges tend to move on the surface. This is actually a property of Venn diagram generator also. These conductors do not carry any charge inside them, but it's their surface's property. Now we will see the second point. At the surface of a charged conductor, electrostatic field must be normal to the surface at every point. Now we are having this charged conductor, and this charged conductor have E on the surface. Inside the conductor we have defined E to be 0. Inside we have defined E to be 0, but on the surface we have defined E have some value, some magnitude. But in this second case, what they are saying is, if this is the surface area through which we tend to know the E, through which we wish to know the E, then ds and E should be perpendicular or normal. In other words, normal to each other. So this E should make an angle of 90 degrees, should be normal to the surface. This is surface and this is our electric field. Why so? We will read it. If E were not normal to the surface, it would have some non-zero component along the surface. Now if E is at, this is our surface na, wait a minute, I'll make the proper arrow. this is our surface ds and this is our E. Now this E is making some angle theta which is not equal to 90 degree, which is not equal to 90 degree. Now what we do, we for any vector at a particular angle, we divide this vector into two different components, one along the surface and one perpendicular to the surface. Like this one will give us E sin theta component and this will give us E cos theta component. So if our electric field is not at 90 degree but at some other angle, then it will give a non-zero component along the surface, Now free charges on the surface of conductor would then experience force and move. So when it will give some non-zero component along the surface, this is ds and this is E cos theta, the charges present over here will force this, will feel this electric field and there will be generation of the force. Of course, see how this force is related with our electric field is QE, right? So if these charges are feeling any electric field, they will feel a force also. So due to this force, they will move. If I will push you, what will happen? Will you be keep on sitting or standing wherever you are sitting or standing? No, you will tend to fall backwards, right? So if such kind of force is provided to the given charge, what will happen to the charge? Charge will tend to move. In whatever direction the force is given, in that particular direction the charge will move. So this should not happen. We do not need anything which provides the charges to move and refrain from their static condition. If they are moving, they will again start generating the electricity in it, which is beyond our studies, which we do not want to study in this particular part. So we assume that at this particular point, for knowing the electrostatics, we are not dealing with electrodynamics, we are dealing with electrostatics. So to know this electrostatics, we are dealing with this concept. Now in static situation, therefore E should have no tangential components. So see, for us main thing is the static situation. So in this static situation, E should not have any tangential component. Thus electrostatic field at the surface at every of the surface of charged conductor must be normal to the surface at every point. See, so when this is charged at every point, let it be this or this, this should be normal from the tangential of surface. Tangential of surface, this should be normal electric field. Now this is the tangent of surface, so electric field will be like this. This is the tangent for this surface, so electric field will be like this. Tangent is like this, electric field is like this. Now tangent is like this, electric field is like this. So they are at a 90 degree angle or normal to each other. Normal to each other. Next, for a conductor without any surface charge density, field is zero even at the surface. If there is no charge on the surface, then field at the surface will be zero. Field is a component of the charge. Field is proportional to charge. If no charge, no field. That's it. Okay. So mostly we say there is no charge inside, so E is zero inside, and we say that on the surface we have charge. On the surface we have charge, so we have electric field normal to the surface. In case this charge is equal to zero, the electric field will also be zero at the surfaces too. Now the third point, the interior of a conductor can have no excess charge in the static situation. This is very much important. Like when we are saying it's a static situation, how can there be the excess charges? Very understandable. So this is a conductor, and in this particular conductor, the positive and the negative ions which are being generated, positive and negative ions which are being generated are equal in number. positive ions equal to negative ions. Okay. A neutral conductor has equal amounts of positive and negative charges in very small or surface element. We can go with a volume element if we are dealing with sphere, and if we are dealing with a disk, we can assume a surface element. When the conductor is charged, the excess charge can reside only on the surface in the static situation, follows from the Gauss's law. See, if in this we are providing charges, they will not tend to stay here. They will all go on the surface. They will all go on the surface. And this follows from the Gauss's law. We have read in the Gaussian surface, as you remember, and if you don't remember, kindly go to the chapter 1's last topic, that is application of Gauss's law. In that application of Gauss's law, you will understand that on the surface electrostatic field was defined, but when we took some point inside the surface, we were not able to define electric field. Like, we were able to define electric field which was equal to 0, but on the surface and above the surface there was some value for the electric field, So this follows up from this application of Gauss's law for the spherical shells. Or basically these were the application to make us understand basics comes from the Gauss's law. So you can just go through the last two topics of the chapter 1, that is Gauss's law as well as the application of Gauss's law, to have a better understanding of this particular point. So now consider any arbitrary volume element V inside the conductor on the closed surface S bounding the volume element V. Electrostatic field is 0. Of course inside it is 0 as we have read in point 1. Thus the total flux through S is 0. Now from inside if we are talking, they are saying it is 0. Of course it is 0 because when there is no electric field available, from where will the flux will come? When there is no electric field lines, what is flux? Flux is the amount of electric field lines coming from a particular surface ds. If the surface is internal of a conducting body or a conductor, if a surface is internal, from here if we are talking, E is 0, hence flux is 0. But when we talk about this surface, and this surface is very small, extremely small, but still it will have some value of xi. Why? Because this surface have electric field component. Electric field at surface is not 0. By Gauss's law, there is no net charge enclosed by S. No net charge enclosed by S, so no net charge enclosed implies Q net equals to 0, hence E equals to 0, hence xi equals to 0 for inside of a conductor, but outside, as the excess charge will be stored on the surface of our conductor, so Q will not be equal to 0, hence they will produce some electric field which is not equal to 0, and hence from a very small charged from a very small area component, we can get value for the flux. We can define flux for a very small area. But the surface S can be made as small as you like, that is volume V can be made vanishingly small to get a flux. So from the previous observation we see, this means there is no net charge at any point inside the conductor, and any excess charge must reside at the surface. Now electrostatic potential is constant throughout the volume of the conductor and has the same value as inside on its surface. Till this point we were dealing about the electrostatic field. Now we aim at electrostatic potential V. Potential we have studied in the same chapter, chapter number 2, and we have seen potential is not 0 for any given conductor. So how come that is going, we will see in this particular point. So the potential, as this point says, inside and on the surface, over here and here, the value of potential is V. It is not 0. Since E is 0 inside the conductor, as we have read, and has no tangential component on the surface, no work is done in moving a small test charge within the conductor and on its surface. What we have read in the previous one of the point was that the surface vector and electric field vector are normal to each other. So electric field is no tangential with surface, not tangential with surface, right? With surface it's not tangential. What exactly happens when this is not tangential? They are making a 90-degree angle, and that 90-degree angle actually helps the charge to have no force, right? We have read, as there is no non-zero component along the direction of ds, so therefore no force on the charges. When there is no force on the charges, there will not be any potential on the charges. Sorry, there will not be like any electric field on the charges, and hence the potential will be constant. So this is our conductor, and on this point E is 0, and here E is 90-degree with ds. So in this particular area on the surface and inside, we can move this charge as we wish to move. We do not need to do any work. No work is required in moving this charge from any point from the surface to inside of the conductor. Hence potential throughout this system. There will be some energy, there will be some potential, of course, for any system. So we cannot say that the potential energy or the potential is going to be 0. It is not possible. So there will be some potential, but that potential will be constant. That potential will be constant. That is, there is no potential difference between the 2 points inside or on the surface of the conductor. If the conductor is charged, electric field normal to the surface exists. This means potential will be different for the surfaces and a point just outside the surface. If we deal first, here we talked about inside and surface. Now we will talk about surface and outside On the surface and inside, V was constant, but here on the surface and outside, when these two are compared, V will be variable. It will change. It will have some value at surface and some other value on the outside of the surface. In a system of conductors of arbitrary size, shape, and charged configuration, each conductor is characterized by constant value of potential, but this constant may differ from one conductor to the other one. So when we took a system of conductors, we do not have a single conductor now, but we have many conductors. Hence it is called a system of conductors, and they are having different sizes, shapes, and charge. Arbitrary size, shape, and charge implies no uniformity in the size, shape, and charge. Everything is different. So for each conductor, there will be a constant value of potential. This is one conductor, right? These are conductors. So this will have one value, V1, V2, V3, V4, like that. Every one will have their own characteristic, but will differ from each other. See, a group of human beings, see among yourself, you are too many students in a class. Every one of you have some potential. Someone is good at physics concepts, someone is good at physics numerical, someone is good at both concept as well as numerical but doesn't want to study. Okay, So every one of you is having potential, but everyone's potential is different from each other. Everyone's potential is different for each other. So for one particular conductor in this system, this potential is constant, but for this it is also constant, but both the constants are not same. Okay. So moving on to the next point, fifth, electric field at the surface of a charged conductor. On a charged conductor, we said E inside is 0, but we never said on the surface it is 0. Okay, on surface it is not 0, and how it is defined we will see. This is a vectorial form. To define electric field on the surface, it is given by sigma by epsilon naught into n cap. N cap is unit vector normal to the surface in the outward direction, and sigma is charge density. We have read three charge densities. Do you remember? I will define for you: linear charge density, surface charge density, and density charge. Like this one is for charge density, and here this is volumes charge density. For a given particular volume we define rho. So here we are talking about sigma. So it is a charge density for a given surface. Surface charge density. Epsilon naught is a constant. Now to understand electric field at surface, we will read it in a detailed form. First of all, we consider a short cylindrical Gaussian surface at any point P on the surface. This small Gaussian surface, as seen in the diagram, is known as pill box. Pill box. Like see, we have these kind of boxes in which we store pill. Pills are tablets, the medicinal tablets we take, right? This is one box, and on this we aim at putting a cap, a dhakkan on it. So that dhakkan is also looking like a cylinder. So this is kind of a pill box. Half of it is inside this surface, okay, this surface of conductor, and half is outside. Half inside and half outside. The pill box is partly inside and partly outside the surface of conductor. Small area of cross section del S and negligible height. This is having this particular area as del S, but the height is negligible. Height is extremely small. Height small. Inside the surface, electrostatic field is 0. E equals to 0 inside. E equals to 0 as read before. Outside the surface is normal to the surface with magnitude E. Outside it is perpendicular, ds in this direction, so E is in this direction, and that is not equal to 0. It is having some value. Thus the contribution to the total flux through the pill box comes only and only from the outside. सिर्फ बाहर से we are getting the flux का contribution. Okay, flux contribution, not from inside. Circular cross section of the pill box. This is equal to plus or minus E del S. E del S. Okay, this is E del S, and xi equals to E del S. Now this value is positive. We have taken plus and minus. In what case it is plus? It is positive when surface charge density is positive, and negative when surface charge density is negative. Over here, surface charge density more than 0, that is positive, tends to plus, sorry, that's not P, plus E ds, right? And in case of this, sigma equals to less than 0, that is negative, it will give us minus E ds, right? Since over the small area del S, E may be considered constant and E and del S are parallel or antiparallel. This is a bigger area, E and del S. So this is antiparallel case and E del S. This is a parallel case. Anti-parallel and parallel. The charge enclosed by the pillbox is given as sigma into del S. This is the charge enclosed per unit. This is the charge enclosed per unit area. Per unit area. For a single unit of area, this is the charge. So for this much amount of area, what is the charge? For this much del S, it is unit charge, surface charge density into the surface. So this is the what we will get, sigma del S. By Gauss's law, E del S equals to sigma del S by epsilon naught. This del S and this del S will cancel, and for E we will get sigma equals to epsilon naught, E equals to sigma by epsilon naught. We have taken sigma in the mode, so that we can define it with positive values. It is defined for negative as well as positive value, but for our electric field, the solution should be positive. Electric field cannot be negative. Okay, so electric field is normal to the surface. Like electric field cannot be negative, that implies a negative electric field will be generated for a negative charged ion, and a positive electric field will have positive value for a positive charge. Electric field is normal to the surface. We get the vector relation which is true for both the signs of sigma. For sigma greater than 0 is normal to the surface outwards. This is our surface. If E is outwards, that implies sigma is positive. In case E is inward, going inside the surface of the conductor, sigma tends to be negative. Normal to the surface, inward. Now the fourth one, electrostatic shielding. This is a very important concept. First thing, important concept. And why this concept is important? This is important because we use this concept in protecting many electrical equipments. From varied external electric fields, the fluctuations in the electric field. Okay, so this concept is a applicability based concept which we see in the equipments, the electrical equipments in our household. Like we use fridge, a TV, a bulb, a iron. Okay, so all these things are electrical in nature, and there is a fluctuation of voltage. You have seen, like when it's thunderstorming, the current which is coming to our houses will start fluctuating. Because of this fluctuation, this electrical charges movement is also fluctuates. As the motion fluctuates, the electric field also fluctuates. So suddenly it will get lower down, and suddenly it will start to have a maximum value. So in such a case, our electrical equipment have tendency to get corrupted. They can get an electric shock, can result into overheating of our electrical equipments, which leads to the disastrous results. Like our TV will not start or will not show any signal, can even blast, can have a short circuit inside. So to prevent from like our electrical equipment from such kind of electrical fluctuations, what we do is we provide these electrical equipment with this one like a box kind of thing, which we say as voltage regulator or stabilizer. Voltage regulator or stabilizer. So these stabilizers help in stabilizing the voltages and the electrical motions. Mostly this concept of electrostatic shielding is one of the way to understand how we are protecting. Other than that, the concept of voltage regulation and stabilizers is coming in the upcoming chapters. This voltage regulation and stabilizers, in these one of the concept used is electrostatic shielding, but other than that we have used two more concepts in these. So this electrostatic shielding is not the sole application which is seen in the voltage regulator, so don't take it as a sole thing. For the regulation of voltages and for the stabilizing of the electrical equipment, we use electrostatic shielding as one application, and others we will read when we'll go to the alternating currents and electromotive inductive forces. Okay. So now we will understand what is electrostatic shielding and how it is helping us to shield our electrical equipments or any other electrical component. It can be anything, whatever deals with the external electric fields that needs the protection of the unwanted changes or sudden changes of external electric fields. So this kind of shieldings can be provided. To understand this, we will consider a conductor with a cavity with no charges inside the cavity. Electric field inside the cavity is zero, whatever be the size and shape of the cavity, and whatever be the charge on the conductor, and the external fields in which it might be placed. The electric field inside the charged spherical symmetry of the shell. But the vanishing of the electric field in the charge-free cavity of conductor is very general result. The related result is that even if the conductor is charged or charges are induced on the neutral conductor by the external field, all the charges reside on the outer surface of the conductor with cavity. Whatever be the charge or field configuration outside electric influence of the field inside the cavity always zero. Electrostatic shielding is that. This effect can made use in protecting sensitive instruments from outside electrical influences. So I have went through this whole concept, read line by line. Now it's time to get an explanation for it. We have suggested or we have considered one of the conductor. See over here, this is the conductor. I'll get a highlighter. This is the conductor. In this conductor we have made a electrical cavity. This is the electrical cavity. In this electrical cavity we do not have any charge. In this electrical cavity what we not have? We do not have any charge. Q equals to 0 for this. So there is no surface charge density, no charge density, and electric field is also 0. When Q is 0, we tend to speak like E is also 0, sigma is also 0, and we have a constant potential. Our charges can randomly move if we bring a charge. Okay, if we bring a charge. If we are not bringing a charge, that is not a concept to be read over here. So charge is 0, E is 0. Now we have introduced or induced external electric field. External electric field. Now due to this external electric field, these will be the charges on the surface will tend to align. The charges on the surface will align. Q on surface will align as set against the E. Okay, E is in this way, charges will align in this way. They will be parallel or anti-parallel to each other. Okay. Now external electric field is there, and there is excess charge on the surface. Now we provided the excess charge to this structure, this conductor we are providing the excess charge. When this excess charge is provided, what happens? This excess charge tends to stay on this surface. They never move inside. They never move inside. And as they are not moving inside, they will never reach the cavity or the outer surface of the cavity. Hence, as these charges are being stored on the surface, the cavity will not get any charge. The cavity will not get any charge. As far as the cavity is not getting any charge, there will not be any electric field, any potential, or any charge density in this particular cavity. Now, as the cavity is having nothing, everything is zero, it's protected. It's basically shielded. It's shielded from the outside electrical influences. So this effect can be used in protecting sensitive instruments from the outside electrical influence. Now we will little talk about the various instrument. One of the common example is lift. Okay, this is a lift. Outside the lift we have this space. So, and we have so many electrical wires and these what we say belts, all these things we have tied to this lift to make it a proper motionable lift. So if there is a thunderstorm, lightning struck, electrical uh, damages or short circuits, this will never come inside this lift, because this is a conductor, this is again a conductor, we have layers of conductor on the lift. So whatever charge is coming, they reside on the surface. They reside on the surface, they will never come inside. So a person inside the lift is always safe in case of electrical mishaps. But a person outside and touching this surface can get a good electrical shock. Okay, so never touch the outside of lift. You are protected inside this particular lift. Second is, we tend to make copper wiring. Copper wiring which have like inside they have cavities, and outside they have metals like this. See, so this is metallic, will this is the ends. Okay, I'm not closing. So this is metal, and this is kind of a cavity we have seen here, we have seen in this concept. Okay, so this is cavity. Now the signals passes through this. These signals can be any sort of signals, but as we are talking about electrostatics, we will talk about electric signals. Electric signals. These electric signals are passing from here, and from this outside we are having some external electric fields. External electric fields going to this area. But as this cavity and conductors are there, copper is there as a conductor, this electric field will not influence this signal, will not influence these signals, and there will not be any electrical noise. Electrical noise. So one of the example we saw was earthing. In earthing also we tend to diverge these charges. Mostly we diverge, and these earthing equipments are also using this electrostatic principle. Like these equipments, this is a earthing rod, they will also have some surface cavity inside, so that the charge is distributed on the surface and there is no distribution inside, and the motion is smooth and uniform and travels faster inside the earth. So these are the few of the examples which use purely electrostatic shielding, and other than that many other sensitive equipments use electrostatic shielding, which is a assignment for you to go through and find few other examples. I have given you few 3 to 4 examples of electrostatic shielding, and I hope you will find more electrostatic shielding examples. So for today's class it's all that's all we need to study. But the main thing which we aim from today's class is that these concepts of the physics are a part of conceptual questions. This part is extremely important. This part of your chapter is based on the concepts, and these concepts are helpful whenever you read any application, whenever you go and understand about electric fields and electrostatic potential, it's very much important for you to learn these concepts, because when you are going for your board examination, these concept based questions got a priority. And when you go for your entrance examination, again, these concept based questions are very much important. You will find many questions based on the concept. They ask in a formula based way. It will look like they are asking you a question for a derivation, but they were asking the question from these concepts. They will give you a structure like this and will ask what is the electric field at point A, what is the electric field at point B, what is the electric field at point C, and what is the electric field at point D in the presence of external electric fields. Okay, so you have to understand that in a concept we have read, inside the surface, inside the conductor, this is insides of the conductor, right? Inside the conductor E is 0, so at point B E is 0, at point A it is 0. Why E is 0 at point A? Because it is prevented by the help of electrostatic shielding. At point C we have some electric field, and at point D also we have some electric field. But at point C and at point D, at both these 2 points we have different electric field. At C and D we have different electric field. So such kind of questions they will ask you. They will give value of E at A is Q upon 4 pi epsilon naught into R naught square. At B it is Q upon 4 pi epsilon naught R square. Now you will think that this concept is from the previous section we have read about electric fields, but no, uh, like this concept is from here. At point A, how can we have electric field when this is a concept from the electrostatic shielding? So it is extremely important to know these concepts. So this particular class is very much important for you people. Kindly go through all these 6 uh, properties of this one conductors and electrostatics for conductors, like thrice go through this thing, remember these points, and try to use these applications in each and every question. So it will be extremely helpful. Now these 4 diagrams I haven't explained so far, right? So you may be thinking why I have made these diagrams. So basically this diagram is a review or a summary of the concepts we have read today. Electric field inside the conductor is 0, hence surface charge density inside the conductor is 0. Potential inside and outside on the surface, potential over here and here are equal, because electric field is 0, so there is no work done in bringing a charge from here to here. Okay, so potential on the surface and potential inside the conductor are same and constant. Electric field on the surface, is given in the vector formula by E equals to surface charge density divided by epsilon naught into unit directional vector. Now when we deal with electrostatic shielding, we see for any amount of charge provided on the outer surface of the conductor, there is no charge which is passing to the cavity present inside the conductor, and hence electric field and surface charge density inside the cavity is also 0 and inside the surface is also 0. So this is the electrostatic shielding, which helps uh, in protecting many sensitive electrical equipments. So that's all for today's class. Hope you got a very beautiful understanding of these concepts. If not, please go through the classes once again and learn these 6 concepts by heart it, understand it, and try to use its applicability in various questions you solved so far. Okay, so that's all for today's class. We'll meet in the next class with a new concept. Have a good day, guys. Bye.